Okay, the next assignment is due a week from today, and I double-checked when we're going to start working on WMS. It'll be 2 weeks at the soonest, possibly 2 weeks and 2 days. So there's no real urgency in downloading and installing that. But I will give you the link to where you can get it, as well as the serial number that you'll need to activate so that it works. We're going to be talking about the NRCS rainfall runoff model, and it's kind of an intermediate way between the crude simplicity of a unit hydrograph, which you either have to have measured rainfall data from a certain area, or you can create a synthetic unit hydrograph that's based on basin characteristics. So that's kind of at the crude approximate end of trying to predict what the runoff looks like. The more sophisticated way of predicting what the runoff looks like would be dividing the network up into lots of little mesh elements and individually looking at each one of those finite areas and estimating the infiltration, the runoff, and those characteristics from each of those mesh areas. NRCS method kind of is in between. It takes into account the basin characteristics, but it's on the single basin size all at once rather than breaking it up into smaller pieces. So before we talk about the NRCS approach, the big question of this course, what's the thing that the hydrologist has to say to the hydraulic engineer? How much runoff, right. So how much runoff, and then also when is the runoff going to be? So when we say the amount of runoff, we're not just talking about the volume, but we're also talking about the timing of it. And the timing becomes especially important for storage, for things like flow equalization basins, for storage like ponds. The timing is less important for culverts. Culverts are sized really just for the peak flow rate that's going to be going through them. So the way that I put it, if I was going to distill this course down to like one question that you're learning all of these fundamentals to be able to answer, it's for an area of interest, what are the runoff characteristics? So characteristics get into the amount, the timing, and then also some of the quality issues as well, because the characteristics could be talking about the amount of sediment that's being scoured out of a watershed, could be talking about the nutrient loads, things like phosphorus and nitrogen that are going to be stimulating algae growth in both rivers and like in the Gulf of Mexico. So those characteristics can have a lot of important factors that are all-encompassing. And so if we want to know what are the runoff characteristics, we have to have a description of the rainfall that the area of interest is going to encounter. And some of the data that we need to know about the rainfall would be the return period amount relationship. And so we're talking about 2-year storm, 5-year storm, 10-year storm. And so that's just for a certain probability of occurrence in a given year, how much are you going to see? Now the temporal distribution, remember that there are variations depending on where you live in the country. People who live in the Pacific Northwest experience kind of slow drizzle, might be a way to describe it, where the intensity is less of a peak than here in the Midwest, where we have the type 2 storm characteristics that are typified by that classic afternoon thunderstorm where the warm air rises very suddenly, then it begins to cool, the condensation occurs, and then there's a sudden thunderstorm. So temporal distribution is talking about the amount over time, and then spatial distribution is how much it varies over space. And we talked about how different basin sizes can affect the intensity of storm that you're expecting to see over that wide of an area. For instance, over the entire Ohio River Basin, if we had a table that was showing the probable maximum precipitation for gradually increasing watershed areas. And for a really big watershed, it's unlikely that you're going to have storms over the entire thing, really intense storms over the entire thing. And so the probable maximum precipitation for a large area is smaller than the probable maximum precipitation for a relatively smaller watershed. And that's just because a really intense concentrated storm can only occur over a smaller area. So spatial distribution is another way that we want to have all of this input data that's going to allow us to answer this question: what does the runoff look like? So the NRCS method is going to use rainfall as one of the inputs. I'm sure you've heard of the word algorithm, and I always kind of cringe when I hear somebody say algorithm, because usually the people saying the word algorithm don't create algorithms. They don't really know what they are. It's just kind of like a buzzword that makes people think, oh, this is like important technical stuff. But the NRCS method is using lots of different inputs to describe an output, and rainfall is one of those important ones. NRCS method also somehow takes into account abstractions, although it's not very sophisticated in the way that it does it. There are other approaches that handle abstractions with more resolution. And so the abstractions that I listed here on the whiteboard as being one of the differences between rainfall excess and rainfall includes evaporation, interception, the wetting of surfaces before the water starts to move overland. And so the rate of evaporation during a storm event is going to be relatively low, because if you think about the time scale, evaporation is measured in terms of millimeters over the course of a day. And you looked at evaporation data from New Mexico, and you'll remember that when you looked at that, that was in the order of maybe, I think, 4 millimeters per day of evaporation, maybe a bit higher if you have a really low humidity and lots of wind. But a big peak storm that's dumping a lot of water, it can be several inches. And so we're talking now about maybe 10 centimeters or 15 centimeters during a really significant storm event. And so if you have 15 centimeters of rainfall, the amount of evaporation that occurs, even if it is that 6 or 10 millimeters of evaporation, is going to be relatively small. And so a lot of models just ignore evaporation, because over the long term it's a very significant factor in a water balance. But over the design of infrastructure term, even the course of a couple of days for the sizing of a pond, evaporation would be a minor factor. Interception can sometimes also likewise be overwhelmed. The amount of interception that you're going to see for a 15 centimeter storm event is going to be essentially negligible. Infiltration, though, is pretty important, and every model takes infiltration into account, even the rational method. When Darren was here in class last time, he mentioned that the rational method is one of the 3 approaches they're using for modeling. He mentioned the rational method, TR55. He said that they use some USGS empirical equations, and we'll learn about that in a couple of weeks. And so the rational method says that there's some C value, and all of the losses are lumped into that C value. But if you look at a table of C values, the main factor that it accounts for is differences in soil type and land use. Those tables are saying, you know, a grass surface versus a pavement surface, or roof area versus crops of some sort. And sometimes they'll have slopes built into those C value tables. Sometimes they'll get to the soil type that the different crops are planted on. But in the rational method, soil type, land use, and then this antecedent moisture condition is talking about the prior rainfall events before the one of interest. And so infiltration is really strongly affected by that. So on the left, these are the things that go into the model. You can think of this as the raw data that you have to go and gather for a watershed before you're able to do any kind of prediction on what the runoff characteristics are. And once you have that raw data, then you use some sort of a modeling to equate rainfall to runoff. And so There may be ways to estimate the rainfall excess by quantifying the difference between rainfall abstractions and infiltration. And then the shape of the hydrograph comes from either a unit hydrograph, or it comes from like observed unit hydrograph data or synthetic unit hydrograph data, or just typical patterns. And I showed you the typical rainfall patterns, and I mentioned type 2 just a moment ago. There were these curves that looked like this. The storm started relatively slow, then went to a peak, and then it gradually slowed down, and it was 1.0 on the axis, on the vertical axis, where it's just the fraction of the precipitation, and it was a 24-hour time period. And so this was kind of like a typical temporal distribution of rainfall. There are typical runoff patterns as well. And the NRCS method says there's this standard hydrograph shape that it comes to a peak and then it takes a little bit longer to drain back down to zero. And so it's not as crude as the triangular unit hydrograph. You know, when we were making synthetic unit hydrographs with the Snyder method, we said it's a triangle. And even though we maybe made the base leg 1/3 of the storm, and it would 2/3 after the storm to kind of have a slower drainage, still the triangular distribution is less realistic than in the NRCS method, where we're using a unit hydrograph shape that is based on lots of observed storms in a variety of different conditions. And so then all you're trying to do is figure out how big the peak is and how long the storm lasts to then apply that shape. One of the factors that determines how long to make that hydrograph is to look into the accounts of the effects of routing. And the routing means the delay that occurs as the water moves through the basin. And so the sinuosity of the streams, meaning how meandering they are versus how straight they are, is an important basin characteristic. The shape factor, meaning how long and skinny the basin is versus how fat and wide, and the density of the drainage. We talked about some of those general factors, also related to the roughness of the surface, the slope, and so on. So basin characteristics are important for routing, and that routing describes how long it takes until the rainfall produces the peak. And we use all that data for sizing of hydraulic structures, and we haven't yet talked about it, but we will towards the end of the course. We'll begin discussing risk assessment and how to analyze the value of providing flood protection. And so we'll kind of combine some ideas from engineering economy, where we do benefit cost analysis. We'll look at what is the benefit of avoided flooding relative to the cost of providing that protection. So, risk assessment is a really big thing in their, entire master's degree that are focused just on risk assessment in hydrology. And so, unfortunately, we'll have to speed through it in about a week, but it'll be a first exposure of some of the implications of the runoff characteristics. So, like, this is the 10,000-foot view, and we pause now in the course to kind of refresh our understanding of this, because we're kind of at that inflection point between learning all of the theory and the application of the theory through a few more sophisticated hydrograph generating tools like the NRCS method. So here's just another way of conceptually kind of graphing all the ideas together. We have rainfall and we want runoff. And so there's got to be something in between. The model is a way of having the input data that may be a temporally distributed, like a hydrograph. By the way, one of the quiz questions that I didn't give you today, I was going to ask it, but I thought, it's too easy. They'll definitely know it. There's no point asking. What's the difference between a hydrograph and a hydrograph? So the hydrograph would be an illustration of the temporal distribution of rainfall. And the hydrograph is what characterizes the temporal distribution of runoff. So we've got something in between those two. So we start with a hyetograph, and we want the hydrograph, so the model connects the dots between these two things. So the factors that are going to go into the NRCS method will be some estimation of the soil that's there, because the soil and the land cover affect the infiltration. Infiltration is one of the biggest differences between rainfall excess and rainfall. We're also going to account for the abstractions. The slope can be in there, the stream characteristics, and then the shape. So all of these factors are taken into account by the model when it translates what the rainfall response looks like to the runoff from the watershed. So it's going to define both the sand and soil characteristics. And the nice thing about both of these is that we can go to data sets that are online, and it takes kind of the burden off of us. Engineering judgment is developed over the course of a career, and sometimes people with a lot of experience can go into the field and just by looking at what types of soils are there and by looking at the type of vegetation, kind of develop an intuitive feel for what the runoff characteristics are going to be like. But they can only maybe apply that to what they can see. And watersheds are sometimes hundreds or thousands of acres. And so a better approach is, what's more data-driven, is to use GIS, where people have gone through and created soil maps and have gone through and with aerial photography identified where are their roads and how much of a watershed is road versus how much of it is maybe residential area, how much of it is commercial property. And so there are maps we can download in a thing called the National Map Viewer. We can get the soil and land use characteristics and kind of automate that analysis, and it takes the burden off of us, and it improves the defensibility of a watershed model. And that's another thing that Darren kind of hit on during his description of what they do at DOH, is they get sued a lot. I hope nobody here ever gets sued. I haven't been sued yet, although I had one project when I was a real young engineer I thought for sure was going to fail. It was a situation where a client, before they hired us, they knew what size pipe they wanted, and they knew that they wanted it to be plastic. And so, I mean, there really wasn't any wiggle room. They wanted two 42-inch diameter culverts going under a certain roadway. So we said, okay, that's what you get if that's what you want, two 42-inch culverts. But it was a big plastic pipe. So 42 inches is 3.5 feet diameter pipe. So and you'd have to hunch over to get through it, but they were big plastic pipes. They only had about 6 inches of cover from the road to that plastic pipe. So I thought for sure, some truck's going to drive over that and it's just going to collapse. It never collapsed while I worked at that firm. So if it collapsed later, I'm not sure. The point is defensibility, when you're doing engineering design, you have to be able to say, this is why I did it, and this is a good, legitimate reason. And because the client asked for it, wasn't a very strong reason why we did it that way. But if you're basing your watershed model on a standardized, accepted data set of land use and soil type, then that improves the defensibility of your work. And so that's what we're going to ultimately work towards, is not just guessing a C value based on what we look at the watershed and saying, well, maybe it's a C value of 0.6. We'll take the guesswork out of it, and we'll calculate something called a curve number in an automated way. And a curve number takes both land use and soil type into account. And it's used in the NRCS method to describe the relationship between runoff and the rainfall excess that goes on top of the surface. So the other thing that the NRCS method is doing is it estimates the distribution, the timing of it. So when these different things kick in, like when the initial abstractions are satisfied, when the runoff will occur, and it translates the flow from the runoff depth using a unit hydrograph. So here's the model. This is a conceptual model. And what it's saying is the first precipitation that you see, we're looking at a hyetograph to begin with. This blocked bar chart, this is when the rainfall occurs. So you can see over here on the vertical axis is saying precipitation rate. There's a certain amount of the precipitation that is satisfying the initial abstraction, and that's what I sub A stands for. It's stored in the catchment before runoff begins. So after the surface wetting occurs, after the building gets wet, after the trees get wet, then there's going to be some amount of the rainfall that satisfies the retention. And so retention, F sub A, is mainly infiltration, but it also includes some local storage. Now this line, this declining curve should look, the shape of that should be familiar from when we were doing like the green amped discussion and the Horton method. It's the declining rate of potential infiltration. And so what it's saying is that there's precipitation, and everything above this declining rate of potential infiltration is rainfall excess. And so here they call that P sub E, precipitation excess. Now the difference between precipitation and rainfall, obviously there are other types of precipitation besides rain. There's sleet, there's hail, there's freezing rain, which hits the surface as ice, there's snow. But everything except for rain gets into the soil and causes runoff at a slower rate than rainfall does. And so rainfall is kind of like the worst case scenario of precipitation. So anything else is going to be less of a problem, with one little asterisk aside that. And that is that if you have snow and it gets warm really fast, then you can have suddenly more water releasing from a watershed than could ever occur during a rainfall event. So just as an example, up in Milwaukee back in the early 90s, they had a really, really snowy winter, and then suddenly a huge heat wave in the spring caused there to be a lot of runoff going into the streams, and all that runoff from agricultural fields took a pathogen into the streams near Milwaukee called Cryptosporidium. And Cryptosporidium is kind of closely related to Giardia. And if anybody here is like an outdoorsman or a camper, maybe you've heard of people getting Giardia before when they go camping and drink from a stream. It's a parasite. So back to Milwaukee, what they had was lots of snow on the ground. It got hot really fast and tons of runoff, so much that the scour and the sediment transport was a lot higher than it usually would be. And so all this Cryptosporidium from basically from cow manure got into the streams, and the water treatment in Milwaukee had no way to deal with it. And about a quarter of the population of Milwaukee got this Cryptosporidium disease, and it makes you really sick for like several weeks. It's pretty nasty. So like that's kind of a famous case study in water quality and drinking water treatment. It made a lot of federal rules enforced by the EPA came out as a result of that incident. So to the discussion of rainfall versus precipitation, usually we're just going to assume that when we're sizing infrastructure, rainfall is the worst case scenario. So sometimes we use those two things interchangeably, precipitation or rainfall. But here, technically, P sub E it stands for precipitation excess. So what we're saying is that the water is going to be in one of three places. The precipitation is going to be the excess, and that's what can run off, because it's the leftover after the initial abstraction and the retention have been satisfied. So this is a mass balance equation. This P equals P sub E plus IA plus F. This is kind of like the continuity equation that you learned back in fluid mechanics, and that is, flow in equals flow out. So here we're saying that if there's runoff from a watershed, it's because of precipitation minus the other things that didn't run off. So this is how the NRCS method kind of conceptually conceives of what's going on inside of the watershed. It's saying that the water's tied up in three places. Now here is an equation that relates those three quantities. It's saying that the ratio of retention to something that we're going to calculate as storage, the potential maximum retention. So this S we can calculate with a related curve number property that the curve number is related to the land use and the soil type, and there are tables of data that says for certain soil types and certain land uses what the curve number is going to be. So I'll show you how to calculate S in just a moment. But the model says that the ratio of those two things is the same thing as the ratio of the runoff to the difference between the precipitation and the initial abstraction. So in other words, the amount that's actually stored versus the potential storage that could occur. Now, we said that in this conceptual model, the first thing that's satisfied is the initial abstraction. Before there's any runoff, there has to be the initial abstraction. And it turns out that that's really tricky to characterize, because you think about all of the things that we lumped into the initial abstraction, where we were saying there's the evaporation, which we kind of ignore. There is the surface wetting, the wetting of plants, tree leaves, and that varies seasonally, of course. And so what they do is just to approximate the initial abstraction as 20% of the storage. So I'll show you how we can calculate S, and then once you know S, you just, as a starting point, maybe would assume that the initial abstraction is 20% of that. Okay, so I mentioned the continuity equation and referred back to fluid mechanics when we were studying in versus out. And here's in a mass balance, the in should equal out unless there's either some accumulation inside of the control volume or some release. And so if there's a net accumulation, then out will be less than in. We think of it like as a tank. If the tank is filling, then out is going to be lower than in. If the tank is draining, out can be greater than in. And what's inside of that tank? The tank is our watershed. That's the control volume. And how much storage it has is the initial abstraction and the retention. And so these two terms are the accumulation that makes for the difference between the rainfall and the rainfall excess, which is runoff. So here is the formula for storage, and storage is measured in inches in this formula. The tables that you can get in hydrology textbooks and from federal highways or from the USDA, the curve number tables are formatted so that they go up to 100, and then that gives you a storage quantity in inches. Now once you have the storage, then the way that you calculate in the NRCS method the rainfall excess, P sub E, is with this formula. And if you have the precipitation is greater than the initial abstraction, so remember 0.2S is how we account for the initial abstraction. What we're saying is if you don't have that satisfied, there won't be any runoff. So if the precipitation is less than 20% of the storage, then we assume all of the precipitation is just gobbled up by the initial abstraction. But once you've satisfied the initial abstraction, then this formula will kick in, and it will tell you how much rainfall excess you're going to see depending on the amount of precipitation and the amount of storage that there is. Okay, so let's crunch some numbers here, get a feel for how this equation works. Let's say that we either have a calculator, spit it out, or we go to a table and we get some curve number data for a watershed. Later on we'll learn how to get that curve number data, but for now it's just given. If the watershed curve number is 70, then how much rainfall excess will there be in the first storm, which is a relatively small storm, 0.7 inches. And then for part B, let's look at if the storm is much larger. For a 3.5 inch precipitation, how much rainfall excess is there, and then do the mass balance. You know, in addition to identifying the rainfall excess, identify how much of it went to initial abstraction, how much of it is infiltrated, and so on. So remember, the first thing you have to do is compare precipitation to the initial abstraction. And so for part A, the question is this 0.7 inches of rainfall going to be more than 20% of the storage? Okay, the smaller storm, where it's 0.7 inches, it doesn't accomplish the initial abstractions, as the book would put it. If we look at from the storage, the potential maximum storage based on the land use and soil type that's kind of all rolled up into the curve number, it tells us that the watershed has the potential to hold on to 4.286 inches. Now, that's over a long period of time, by the way. It's not that all of that storage has to be accomplished before there's any runoff. That's just what we're saying the initial abstraction is. So we're saying, as an approximation, 20% of that storage has to be filled before there will be runoff. And so 20% of that 4.286 inches is 0.857 inches. So in this case, if you have 0.7 of an inch of rainfall and 0.857 inches of initial abstraction, there won't be any runoff from that. On the other hand, that other storm, for 3.5 inches, there will be rainfall excess because the precipitation is greater than the initial abstraction. So then the question, now we can start to use this P sub E formula, is how much rainfall excess will there be of that 3.5 inches? So it should be about an inch, 1.008 inches. Of rainfall excess. And so the next part of the example was asked, by the way, before we move on to where is the water, just any question on the example up to this point so far? Okay, so where is the water is asking, let's do this mass balance. Let's find out the rainfall, the abstractions, the storage. Where is it? If we've got 3.5 inches of precipitation and our initial abstraction is 0.857, and here is the precipitation excess, we could just double check the F sub A by substituting in the storage and the rainfall excess that we've already calculated, the precipitation and the initial abstraction. So the F sub A is representing the retention inside of the basin. And so that's mostly infiltration. And so we can get that that's 1.635. And that's the same thing that you would have got if you'd simply subtracted 3.5 minus the initial abstraction minus the precipitation excess. If you'd just done subtraction from that, you'd get 1.635. And so this is just kind of confirming or calculating a different way the difference between the rainfall and the runoff. So this is a model. Remember, a model is just some sort of approximation of reality. And there's essentially 4 moving parts in this model. The moving parts are the precipitation, the initial abstraction, the retention, and the rainfall excess. Any questions before we move on? So this gives us the amounts, but we haven't yet talked about timing. This is just going to tell you for a certain amount of rainfall. You'll notice that this didn't say what was the intensity, and this didn't say what was the duration of the storm. So far, there's no time component to what we've calculated. It's just strictly quantities. So it's not really to a useful state yet. We've already seen all this. Oh, okay, here's a hint for the homework. For problem 3 on your next homework assignment, use a cumulative precipitation up to a certain time, and this formula can be used for the precipitation at that time. The initial abstraction will be a fixed quantity, and the storage is a fixed amount, but what we're saying is that you can find how this applies at many different times. The storage at a certain time is going to be dependent on the precipitation at that time. So just essentially translating this to some precipitation at the time specified in the problem. So refer back to that as you're working on the homework 8, problem 3. Okay, so the two things that we still need to talk about with this NRCS method is, number one, where do the curve numbers come from? And then number two, how do you translate the amounts into rates, into runoff rates? And so essentially, like, what's the time component of when the water's coming out of the watershed? Curve numbers are classified first by characterizing the soil type. And there are so many different discrete soil descriptions that we'll take a look at when we start looking at GIS data from the area around here. With the soil mapper that we have access to, you can click on an area, and these soils have names that are sometimes tied to the region of the area, like the era that the sediments were deposited and so on. But what the NRCS method does is defines soils in terms of their infiltration capacity. So group A soils are defined as those that have a minimum infiltration rate between 0.3 and 0.45 inches per hour. Now, their maximum infiltration rates can be considerably higher than that, but their minimum infiltration rate is after all of the voids have been filled, after that initial suction pressure has decreased, essentially how much the soil is just draining by gravity. And so type A soils are usually very coarse sands, aggregated silts. I don't want to say that because I'm not sure of the pronunciation. Loess? Any soil nerds want to? All right, we'll all agree on that. So type A soils are essentially heavily granular. On the other end of the spectrum from clays, D soils have essentially no infiltration rate because they are heavily plastic, really heavy clay or saline soils where there's the salt in the soil contributes to the water being bound. What we see most of the time around here are group C soils and occasionally group B. Group A soils are pretty uncommon in Cabell County at least. You can see that group C soils have some clay in it, and there is some infiltration rate, but not a lot. It ranges starting at 0 for the minimum infiltration rate. So the name of the data set that we're after to get this when we go to a GIS database it's called hydrologic soil group. And so the hydrologic soil group will tell us this A through D rating. And then we combine the hydrologic soil group with these land use descriptions. And so you can see, for instance, that in an urban area that has lawns that are in good condition, you would go over here, and here's a description of what they mean by good condition, that the grass is covering 75% or more of the area. So depending on what soil is underneath that grass, the curve number is going to vary. Now, one thing I need to mention is that these curve numbers that you see in this table are for kind of like middle of the road moisture conditions. These are called type 2 curve numbers, where it's not that it's been an extended dry period, and it's not that it's been raining in the immediate days prior to when we're interested in. It's just there's a typical amount of soil moisture. because sometimes we have to convert between these typical soil moisture amounts and the other ends of the extremes. We can get different curve numbers if it's been really wet, or certain curve numbers if it's been really dry. But if you'll notice, the trend is you have a higher curve number with a clay soil. You also have higher curve numbers for lots more paving. So look here at paved with curbs and storm sewers. So paved areas, the curve number is independent of soil type because it's the surface itself that's causing runoff, not the fact that there may be clay under the surface. The vegetated surfaces are more heavily dependent on what soil lays beneath. Here is some curve numbers for undeveloped areas. This comes from your text in Chapter 8. So you can see there are curve numbers for woods. That's what we have around here. I think that the difference between woods and forests is that the woods are usually closer to human development, and it may be roads that are cutting into the wooded areas, because when you put a road in through a wooded area, vines and shrubs grow in the border of that wouldn't have been there if it was uninterrupted, like forest land. And so there is a technical definition that differs between the woods and the forest lands. And you'll notice that woods usually have a slightly higher curve number than forest land would. So we have these curve numbers, and what we'll get to when we meet again on Thursday is how to translate what remains, the amounts, into timing, and then also adjusting for moisture conditions. All right, so you didn't get out early when Darren was here to speak. You are getting out early today. I hope that now the debt is repaid. I'll try not to steal your time in the future. I'll see you on Thursday.